Hey everyone, today we are going to be going over projection of moments. So before we really get into this, I want you to think back to the section where we projected forces for a minute. And hopefully you can remember all that stuff about dot products and what it really means to project a force onto a different axis. Now, projecting moments is a very similar concept. We're just going to take a moment that a force creates and project it onto some axis somewhere within our problem. Now, the way that we do this is a little bit different than projecting forces, but it's still the same overall concept, same overall idea. So what we have here in this problem is a force connected down at C. So we have our rod here, and then there's a force attached to the end of the rod, and we're given the XYZ components just to make it a little easier on us for a nice example problem. And what it wants us to do is find the moment in Cartesian components that is acting on this axis AB. So really what we have to do first is we have to find the moment that this force creates about some point on this axis. And we know to do that we use a cross product. And then we have to use a dot product to project that moment onto this entire axis. Okay? And we're actually going to use a method that combines a dot product and a cross product. I'll explain that as we go through it. Hopefully it will, make sense. It won't be too difficult to grasp. But there are a couple things that we need to do first. So, looking at our problem, I'm just going to write out the basic form of what we're going to do. So, to find a moment first, we'll use a cross product. And we always use R cross F, right? To make this nice and easy, I'm just going to use point A. Okay, so we have R, AC, crossed with our force. Then we're going to dot that with our axis AB. Okay? And if you remember back to forces, the axis was always represented with a unit vector. So actually, let's write that here. Dotted with the unit vector of AB. Okay. So that's what we're going to do. We're going to take this cross product, and then we're going to take this dot product. And actually, we're going to combine them both in the same thing. But we need all of these things first. So let's just find the position vector from A to C first. Okay. So if we look at the problem, point A is here, point C is down here. In the x direction goes 3 over, so that is positive also. 3. In the y direction, it comes out 4. Okay. And it goes down 2 in the z direction. Again, I'll apologize for the board drawing. I'm not the best at 3D problems, but when you do these in the book, hopefully you'll be able to see what's going on a little bit better. Okay, so now we have the position vector from A to C for our cross product. We also have the force given in Cartesian components because I want it to be simple for us. So the force equals 10, 20, 30. Okay. So that's the easy part. Those are done. Now let's do the unit vector from A to B. Before we can get the unit vector, of course, we need the position vector. So RAB equals, okay, comes over 3 in the x, comes out 4 in the y, 3, 4, and then there is 0 z component because it doesn't go up or it doesn't drop down. Okay. And the other thing we need to complete our unit vector is the magnitude of AB, which is 5. 3 squared plus 4 squared, take the square root of those, equals 5. Okay. So what we do next is we calculate our unit vector. So unit vector of AB equals 3 over 5, comma 4 over 5, comma 0. Okay. And let's actually write these over here so we have a little bit more room to work with. Hopefully you can see these all right. Okay, so let's think about a normal cross product for a second. And again, I'm going to use the method that I was taught, and this is actually where this method comes in handy, personally for me, I think, because it just makes it nice and easy to visualize this next part that we're going to do here. So, let's just actually make up our own cross product for a second. We'll have 1, 2, 3, 4, 5, 6. Okay? And normally to do this, we'll have equals, equals, negative, and equals. All right. Cross out the first line, 2 times 6 minus 3 times 5. Okay, and then over here we have the I. 1 times 6 minus 3 times 4, so 6 minus 12. And that's going to be k. And then cross out the last line, 1 times 5 minus 2 times 4 is 5 minus 8. And that's j. So notice I put these I, j, and k there. Normally this represents the x, y, and z components, right? Vector I is 1, 0, 0, vector k is 0, 1, 0, and vector j is 0, 0, 1. Sorry, I mixed these two up. I, j, k, excuse me. The vector j is 0, 1, 0, the vector k is 0, 0, 1. So it's like we're multiplying whatever we got here by this I, multiplying whatever we got here by this j vector, and multiplying whatever we got here by this k. Well, we're going to replace those with the unit vector of our axis now. So let's set up our cross product that we're actually going to do. So replace I, j, and k with our unit vector. So I now becomes 3/5. J becomes 4/5. And k becomes 0. And then underneath that, we do our position vector, 3, 4, 2. And then under that, we do our force vector, 10, 20, 30. Okay. And we have equals, equals negative, and equals. So for the first one, cross out the first line, 4 times 30 minus 2 times 20 And then that's going to be multiplied by this one up here. Remember where we multiplied the other one by the I? Now we're multiplying by what we replaced I by, which is width, which is 3/5. Okay, and then we have, cross out the second row, 3 times 30 minus 2 times 10. 20. And we're multiplying that by 4/5, what we replaced j with. Okay, for this last one, cross out the last row, 3 times 20 minus 4 times 10. We multiply that by this one over here, which is 0. So what this is really doing is saying, I'm going to take this first term, multiply it by the first, or take this first x term of our moment, multiply it by the first x term of our unit vector, then take the first y term of our moment and multiply it by the y term of our unit vector, and same with the z. Now that sounds a lot like a unit, or a dot product, right? Multiply the x's, multiply the y's, multiply the z's. There's just one other step that we need. Add them all up at the end. So we do plus, plus, plus. Okay? So this over here is going to equal 48. And this over here is going to equal negative 88. And this one down here, of course, is going to equal 0. So what we have to do is add 48 and negative 88, which comes out to 40. So the moment that is projected onto this axis AB is 40 in whatever units we're using. We're not specifying that right now. Okay, but the question asked originally for that moment in Cartesian components. Right now it's just a magnitude of 40. So we still need to break it up into its moment about the x-axis on the axis AB, and then moment about the y-axis. And we know that the moment about the z-axis is 0 because there's no component of that axis acting in the z-axis. Anyway, hopefully that made sense. So to do that, we just multiply this magnitude back through our unit vector. So 3/4. I'm sorry, that's 3/5, not 3/4. 3/5, 4/5, and 0, because this is the unit vector of our axis. This is describing the direction that our axis is going in. So it's also going to describe basically the direction of the magnitude, or the direction of the moment, you can kind of think of it as. So our final answer is moment about A, B equals 24, 32, and 0. So 24 is acting on the x-axis on our axis, and 32 is acting on our y-axis on this axis AB. And there we go. Hopefully you were able to follow all this. I know it's kind of one of the more in-depth things that you go through in this class, but if you need to, come back, watch the video again, rewind, watch the parts that don't make sense as many times as you need, and hopefully you guys can get this down. Anyway, I'll see you next time.